The truck you're about to see doesn't fit on any road. It doesn't drive to a gas station. It can't legally operate on any public highway in the world. And yet, it is arguably the most important vehicle on the planet, because without it, the copper in your phone, the iron in your car, and the coal that powers entire regions of the world simply would not exist. We're talking about haul trucks that weigh over 500 metric tons when loaded. Machines so massive that a single tire stands taller than most garage doors, costs $42,000 to replace, and wears out in 12 months of continuous operation. These are not ordinary vehicles that were made bigger. They are purpose-built mechanical giants, engineered from scratch to carry the uncarriable. This is how they're made. The mining industry moves approximately 40 billion tons of earth and ore every single year. And let that number sink in. That's more than twice the weight of all water in the Amazon River system, moved annually, systematically, by fleets of machines operating 24 hours a day in open-pit mines across every continent on Earth. The global fleet of ultra-class haul trucks numbers in the thousands, with manufacturers like Caterpillar, Komatsu, and Liebherr, each producing machines that can haul payloads between 300 and 500 metric tons per trip. A single Caterpillar 797F, the most widely deployed truck in this class, costs between $5 and $6 million. The world's largest active copper mines operate fleets of over 70 of these machines simultaneously. The combined payload capacity of a single mining fleet can exceed 30,000 metric tons per shift. That is the weight of a fully loaded aircraft carrier, moved in hours, not years. Not with an assembly line, not with a conveyor belt, or with a frame so large that it cannot be manufactured as one piece. The main frame of a 797F is constructed from high-strength quenched and tempered steel. Steel that has been heated to extreme temperatures and rapidly cooled to achieve molecular-level hardness that ordinary structural steel cannot reach. The frame arrives at the assembly site in sections, each piece weighing between 10 and 40 tons, transported by flatbed trailers that themselves require special road permits. Now, welders, certified to aerospace-grade specifications, spend weeks fusing these sections together using semi-automated robotic welding systems, supplemented by hand finishing on complex joints. Every single weld is then inspected using ultrasonic testing, the same technology used to detect cracks in aircraft fuselages. One compromised weld on a haul truck could result in a catastrophic frame failure under load. And when your load weighs 500 tons and you're descending a 10% grade ramp inside a mine, catastrophic means exactly what it sounds like. Think of the frame as the spine of the machine. Everything else, the engine, the suspension, the body, connects back to this structure. If the spine fails, the entire $5 million machine becomes a pile of unusable steel in the bottom of a mine. The Caterpillar 797IEF is powered by a CAT C175-20 diesel engine producing approximately 4,000 horsepower. For reference, a Formula One car produces around 1,000 horsepower. This engine alone weighs 10,500 kilograms, heavier than an empty school bus. The block is cast from compacted graphite iron, a material that is 75% stronger than conventional gray iron and allows the engine walls to be thinner, meaning the engine can be both lighter and stronger simultaneously. Assembling this engine is itself a multi-day process conducted in climate-controlled facilities. The tolerances involved, the precision with which each component must fit, are measured in microns. A human hair is approximately 70 microns thick. Engine components in this class are machined to tolerances of 5 microns. When the engine fires for the first time after installation, it runs on a break-in protocol at reduced load for several hours, while sensors monitor oil pressure. at combustion temperature and vibration signatures across 200 measurement points. Any deviation outside parameters, and the engine is pulled for inspection before the truck ever moves. The fuel consumption at full operation? Roughly 1,300 liters of diesel every 24 hours. That is a fuel tanker truck's worth of diesel, consumed by one haul truck every single day. This is the part most people never expect. A 500-ton haul truck is not mechanically driven in the traditional sense. It is, in fact, a diesel-electric hybrid, one of the largest ever built. The diesel engine doesn't connect to a transmission. Instead, it powers two massive AC alternators that generate electricity, which is then fed to electric traction motors mounted directly inside each of the two rear wheels. These are called wheel motors. Each one weighs approximately 3,700 kilograms. Each one produces up to 1,450 horsepower independently. But this system, called electric drive, eliminates the need for a conventional transmission, which at this scale would be mechanically impossible to build reliably. It also gives the truck something extraordinary: regenerative braking. When the truck descends a loaded ramp inside the mine, the wheel motors reverse their function and become generators, converting the kinetic energy of 500 tons moving downhill back into electricity. That electricity is fed to a bank of resistor grids mounted on the rear of the truck, visible as large rectangular fins, which dissipate the energy as heat. In newer hybrid designs, some of this energy is captured in capacitor banks and reused, reducing fuel consumption by up to 8% per cycle. Over a fleet of 70 trucks operating 350 days per year, that 8% translates into millions of dollars in recovered energy annually. So each rear wheel of a 797F sits on a suspension cylinder that contains nitrogen gas and hydraulic oil. These cylinders are not springs in any conventional sense. They are gas hydraulic accumulators, essentially giant shock absorbers, each capable of absorbing the impact of 250 tons hitting a pothole at 30 kilometers per hour. The rear suspension cylinders alone stand over 2 meters tall when unloaded. When the truck is fully loaded, then they compress by approximately 30 centimeters under the combined weight of payload and machine. On a bad road surface inside a mine, and mine roads are never smooth, these cylinders cycle thousands of times per shift. The fluid inside heats up. The nitrogen pressure fluctuates. Sensors continuously monitor suspension pressure, and if a cylinder loses even 10% of its rated pressure, the onboard system alerts the operator and schedules the truck for maintenance at the end of the current haul cycle. A blown suspension cylinder on a loaded truck doesn't cause a blowout the way a car tire does. It causes the entire frame to shift asymmetrically under load, which can damage the frame, misalign the wheel motors, and in extreme cases, cause a rollover. On a ramp inside an open pit mine that may be 400 meters deep, rollover is not a recoverable situation. The body of a 797F is not welded to the frame. It pivots at a rear hinge and is raised by 2 hydraulic cylinders for dumping. The same basic concept as a construction dump truck, except the cylinders are each the size of a small tree trunk, and the body itself weighs approximately 60 tons empty. The steel used in the body floor is 45 millimeters thick in the high-impact zones, areas where blasted ore from the mine face is loaded by shovels with buckets capable of moving 60 tons per scoop. When a 60-ton bucket of rock drops into that body from a height of several meters, the impact is absorbed by the body's geometry, a curved, angled design that distributes stress across the entire structure rather than concentrating it at the loading point. Some manufacturers now line the body with specialized rubber impact liners that reduce noise, decrease body wear, and add a surprising benefit. Ore sticks less to rubber in cold temperatures, and reducing the amount of material left in the body at the dump point. That residual material, called carryback, can accumulate to several tons per cycle in conventional steel bodies. Eliminating it increases effective payload capacity by 2 to 5%, which across a full mining season adds millions of dollars in recovered ore throughput to a mine's operation. When it all comes together, frame, engine, electric drive, suspension, a body, and the assembled machine is powered up for its commissioning test, it is one of the most disorienting things an engineer ever witnesses. Something that weighs 297 tons empty, stretching nearly 15 meters long and standing 7 meters tall at the cab roofline, should feel heavy and slow. Instead, it moves with an eerie, almost unsettling smoothness. The electric drive responds instantly. The suspension absorbs everything. The truck accelerates to its operating speed of 64 kilometers per hour on a level surface in well under a minute. And then it disappears into the mine, into a hole in the earth so vast that if you stood at its rim and looked down, the trucks at the bottom look like toys. The copper in your phone had to be moved out of the ground, the iron in your refrigerator, the lithium in your laptop battery, and every gram of extracted mineral that enters the global supply chain passed through machinery like this. Through a payload bed, through a wheel motor, through the welded spine of a machine, built to carry what nothing else on Earth can carry. The next time you pick up your phone, consider the chain of events that delivered even its smallest components to your hand. And ask yourself, what else in your daily life is powered by something you've never thought to look at twice? If that question interests you, there's more where this came from. Subscribe.